Good day, everyone. We are from Group 11 and we are here to discuss Thomas Kuhn, The Structure of Scientific Revolutions, mainly the chapter 4, 5, 6, and 10. We hope you are doing well and sound as you are about to discover another great topic from our philosophy class. So sit back, relax, and enjoy the class. Now, let's talk about who's Thomas Kuhn. Thomas Kuhn is one of the most influential philosophers of science of the 20th century. His 1962 book, The Structure of Scientific Revolution, is one of the most cited academic books of all time. His contribution to the philosophy of science did not only break with several key positivist doctrines, but also a closer look at the history of science. Now we bound to chapter 4, Normal Science as Puzzle Solving. It is said that bringing a normal research problem to a conclusion is achieving the anticipated in a new way, and it requires the solution of all sorts of complex instrumental, conceptual, and mathematical puzzles. We all know that normal science consists in the actualization. This means that we can extend our knowledge by means of having formulated problems that will carry out solution from facts and research. We, especially the scientists, have the will to find for every single solution, even how complex the pattern or mathematical puzzle they may encounter. Puzzles simply employ a special category of problems that can serve to test skill in solution. Puzzles are not just simple tools that we can see as a toy. We can also encounter another type of these, like jigsaw puzzles and more. And in that part, we can see that the problem must be characterized by more than an assured solution, because there are times that we can encounter another set of puzzles and we should know the set of solution to make. In the scientific community, they have criterion for choosing problems, and all of these are assumed to have their solutions. Scientists acquires paradigm to choose problems, and it is one of the things that is taken for granted at all times. The one assumed to have a solution to. However, even if they have this kind of avenue, we cannot change the passion of our scientists to make more problems that they want to solve and explore. That is why having the puzzle must come with rules. Rules that limit both the nature of acceptable solutions and the steps by which they are to be obtained. An example of this is when you are trying to solve a jigsaw puzzle. You cannot just take a photo of it to solve, but rather you need to select pieces of the shapes and see some neutral ground. Photos can be helpful, but there's no guarantee for it to be solved. Gagamit tayo ng iba't ibang rules, like dapat complete yung mga pieces na gagamitin natin. Na-identify natin yung mga shapes at mga sides na piece, and dapat nag interlock yung mga pieces nang walang namimiss na kahit anong host. With this, it is clearly seen that the study of normal scientific traditions discloses many additional rules that allow scientists to commit to deriving their paradigm. Rule establish viewpoint or with preconceptions. Some are the listed rules that relate to normal science in puzzle solving, meaning these are the provided rules that a practitioner of a specialty looks for both the benefit of the world and what science is like. First, generalization, which is the statements that help to set puzzles and to limit acceptable solutions. We can see the conceptualization of problems and their solution accepted by rules. Second, the multitude of commitments, preferably in the sense of instrumentation, are said to be more concrete than the laws and such that we have. Third, quasi-metaphysical commitments, where metaphysics and methodology are seen in this part. Fourth, and the last one, is commitment without which no man is a scientist. They need to be concerned with understanding the world and extending the precision and scope of every science problem they will solve. A strong network of commitments like conceptual, theoretical, instrumental, and methodological are rules related to solving puzzles in normal science. They are highly determined activity, but they need to be entirely determined by rules. Rules are said to be derived from paradigm, but paradigm can guide research even in the absence of rules. Next one is chapter 5, the priority of paradigm. Normal science, rules, and paradigm can be connected by means of community paradigm. In this chapter, we are going to see the priority of paradigms in a lot of ways. Paradigms prior to and more binding and more complete than any set of rules for research that could be unquestionably abstracted from them. Paradigms could determine normal science without the intervention of discoverable rules. There are reasons why there are paradigms in normal science. The presence of paradigm in normal science is visible because of the following. First, people encounter severe difficulty in discovering the rules that guide the specific normal scientific tradition. Naging way ang paradigms para sa normal science na madiscover pa rin ang mga bagay-bagay without discovering what is rules. Kasi sobrang complicated and difficult ng mga rules. Second, it is rooted in the nature of scientific education. These clearly say that science comes with clarity of tools that display with and through their applications. So, ginagamit natin yung paradigm sa scientific education para mas maging malinaw sa atin yung mga unit or like mga research na ginagawa natin. Third, it serves as a guide research as direct modeling of scientific matter. Lastly, as we all know that small or sub-revolutions in science are present, and the presence of paradigms to record differences from different areas is significant. Through this, we are able to understand everything in an easier manner, even though we know how diverse it is. This clearly develops not just our knowledge, but also our discovery of everything. Scientists works from models acquired through education and through subsequent exposure to the literature, often without quite knowing or needing to know the characteristics that have given these models the status of community paradigms. These paradigm figures put a strong grip on securing their function without agreement over rationalization or without the attempt rationalization at all. In a normal science setting, we can note that rules are helpful for us to know the laws, theories, and such to require knowledge that we need. However, the power of paradigm will show the scientists operate with it to get accurate and clear results for solving a problem. Both work well with their given mode of use in the scientific world. Paradigm and rules can be combined for a more influential and knowledgeable learnings. But paradigm can stand alone on itself since nagbibigay ito ng mas accurate at clear na mga sagot sa mga solusyon na hinahanap ng isang scientist. So, yung scientific traditions at paggamit ng mga models ay mas napapadali dahil meron tayong paradigm. So, ito yung priority ng paradigm na dapat nakikita natin. Rules are not neglected, but it's still alive in the presence of science. But mas accurate or mas kinakailangan ng paradigms para nakikita natin yung actual na mga happenings with it. So, now, I'm giving the floor to Miss Bea Mendoza to discuss Chapter 6 and Chapter 10.
Moving on to Chapter 6, Anomaly and the Emergence of Scientific Discoveries. Normal science, described as a puzzle-solving activity, adheres to existing rules and theories. Scientists aim to solve puzzles within the framework of established theories, and this process leads to the steady extension of scientific knowledge. Normal science does not actively seek or produce novelties in facts or theories. Yet it often reveals new and unexpected phenomena and gives rise to radical new theories. The emergence of novelties, despite the conservatism of normal science, is a result of research within a paradigm. This research can be so effective that it ultimately leads to paradigm shifts, where entirely new sets of rules and theories are developed to accommodate the new discoveries. The distinction between discovery and invention is exceedingly artificial. Kuhn suggests that these changes have a recurring structure and are not isolated events. Discovery begins with recognizing an anomaly, the recognition that nature has violated the paradigm-induced expectations that govern normal science. Scientists then explore this anomaly, trying to understand it. The paradigm shift concludes when the paradigm has been adjusted so that the anomalies become the expected. To see how closely factual and theoretical novelty are intertwined in scientific discovery, let's take a look at the discovery of oxygen. In the 1770s, different scientists were trying to understand oxygen. Some were trying to isolate one gas from the other gases in the air, while others, like Lavoisier, were making sense of oxygen in terms of atoms and chemical energy. Lavoisier's discovery of oxygen initiated a paradigm shift. He had long been skeptical of the scientific knowledge he had been taught. Once he started noticing an anomaly, his discovery of oxygen gave shape and form to the new paradigm that would allow him to depart from the existing one. The invention of X-ray also illustrates this kind of discovery from anomalies. Roentgen's discovery began with the recognition that his screen glowed when it should not. If his apparatus had produced X-rays, then other experimentalists must have also been producing those rays, but they ignored it because it doesn't align with their accepted paradigm beliefs. Then, the discovery of the Leyden jar. When it began, there was no single paradigm for electrical research. Instead, a number of theories, all derived from relatively accessible phenomena, were in competition. None of them succeeded in ordering the whole variety of electrical phenomena very well. That failure is the source of several of the anomalies that provide background for the discovery of Leyden jar. The characteristics common to the discovery of oxygen, X-ray, and Leyden jar are characteristic of all discoveries from which new sorts of phenomena emerge. Those characteristics include the previous awareness of anomaly, the gradual and simultaneous emergence of both observational and conceptual recognition, and the consequent change of paradigm categories and procedures, often accompanied by resistance. In a psychological experiment, Brunner and Postman asked experimental subjects to identify a series of playing cards on short and controlled exposure. People were shown normal and anomalous cards. This experiment provides a simple model for the process of discovery. In science, novelty emerges only with difficulty, manifested by resistance, against a background provided by expectation. At first, when scientists encounter a situation, they typically experience it in line with their existing expectations and the usual outcomes predicted by existing scientific frameworks. However, as they become more familiar with the situation or observe it repeatedly, They may start to notice that something doesn't align with their expectations or that it resembles previous instances where something went wrong. The awareness of anomaly opens a period in which conceptual categories are adjusted until the initially anomalous has become anticipated. At that point, discovery has been completed. Let's go now to Chapter 10, Revolutions as Changes of Worldview. During scientific revolutions, scientists see new and different things when looking with familiar instruments in places they have looked before. It is rather as if the professional community had been suddenly transported to another planet where familiar objects are seen in a different light and are joined by unfamiliar ones as well. Only after a number of such transformations of vision does the student become an inhabitant of the scientist's world, seeing what the scientist sees and responding as the scientist does. Each new scientific student's perception of the world is determined jointly by the environment and the particular normal scientific tradition that the student has been trained to pursue. When a paradigm shift occurs, part of the student's world changes. The subjects of the anomalous playing card experiment mentioned earlier in Chapter 6 experienced this transformation. Until taught by prolonged exposure that the universe contained anomalous cards, they saw only the types of cards for which previous experience had equipped them. Yet, once experience had provided the requisite additional categories, they were able to see all anomalous cards on the first inspection long enough to permit any identification at all. Still, other experiments demonstrate that this perceived size, color, and so on of experimentally displayed objects also varies with the subject's previous training and experience. What a man sees depends both upon what he looks at and also upon what his previous visual conceptual experience has taught him to see. The subject of the anomalous card experiment knows or can be persuaded that his perception must have shifted because an external authority or the experimenter assures him that regardless of what he saw, he was looking at a black five of hearts all the time. Herschel, using an improved telescope he had built, noticed an apparent disk size that was at least unusual for stars. Further scrutiny disclosed Uranus' motion among the stars, and Herschel therefore announced that he had seen a new comet. Months later, after multiple attempts to fit the observed motion to a cometary orbit, Lexell suggests that the orbit was probably planetary. A celestial body that had been observed off and on for almost a century was seen differently after 1781 because, like an anomalous playing card, it could no longer be fitted to the perceptual categories, or the star or comet, provided by the paradigm that had previously existed. The minor paradigm change forced by Herschel helped to prepare astronomers for the rapid discovery of the numerous planets or asteroids after 1801. The history of astronomy provides many other examples of paradigm-induced changes in scientific perception, some of them even less equivocal. Another example of this shift in perception occurred with Galileo. While the Aristotelian's view explained the pendulum as a falling object, Galileo saw it as a swinging body that repeated the same motion. This new way of seeing the pendulum allowed Galileo to come up with many critical scientific ideas, such as terminal velocity. Kuhn noted that Galileo's shift of vision partly occurred because of his genius, but at the same time, Galileo was drawing up to the work of earlier scientists who had come up with the impetus theory. His knowledge of impetus theory allowed Galileo to see the pendulum as something separate and specific, and not just a swinging stone. It was a knowledge of impetus theory that allowed Galileo to see the world differently and therefore conceptualize the pendulum. This very usual view of what occurs when scientists change their minds about fundamental matters can be neither all wrong nor a mere mistake. Rather, it is an essential part of a philosophical paradigm initiated by Descartes and developed at the same time as Newtonian dynamics. That paradigm has served both science and philosophy well. Paradigms do not determine single facts or experiences, and so paradigm shifts affect many ideas and observations at once. The same point could be made about any of our earlier examples. To see oxygen instead of the phlogisticated air, the condenser instead of the Leyden jar, or the pendulum instead of constrained fall, was only one part of an integrated shift in the scientist's vision of a great many related chemical, electrical, or dynamical phenomena. Science in a new paradigm involves many of the same techniques, tools, and terms as science in the old paradigm did. However, even when the same techniques and technologies are applied in a new paradigm, they are understood to reveal dramatically different information. Dalton was ultimately the one who overturned affinity theory with his famous atomic theory. Though some chemists were deeply opposed to Dalton's view, this new paradigm quickly proved more useful and efficient. This shift in paradigm illustrated how scientific progress often involves the replacement of a prevailing paradigm with a new and more effective one. And that ends our presentation about Thomas Kuhn's The Structure of Scientific Revolutions. Thank you for listening. This has been Group 11.